know much about give and take till I started listening to the great American philosopher and baseball player by the name of Yogi Berra. So his real name actually was Lawrence. Yogi Berra's name was Lawrence, but he's famous for making very complicated and paradoxical remarks. For example, on this business of give and take, he said, you should always go to other people's funerals or they won't come to yours. So somehow his statements make people think twice and think more than once, but generally it's good for a laugh, including the statement about coming to the fork. He was telling somebody the directions to his house, and he said, take a left, take a right. Then he said, you come to the fork, then you take the fork. So everyone thought funny, and they were giggling, and so was I, till I realized that this is not a joke, because this is exactly what happens in the subatomic world of quantum mechanics. And that's really what I wanted to tell you about, but I realized that I shouldn't laugh at that joke. Then I went to the Yogi Berra website and found all his quotations are all deep statements about physics. I don't have time to focus on all of them, but once I realized that this is no laughing matter, I stopped laughing at all the Yogi Berra jokes. So I'm kind of depressed. There's not much left after that. Anyway, let's not talk about me. Let's talk about you. How do you like my talk so far? Okay. Anyway, some of you do look nervous. I'm not talking about the physicists who really should not be in this room. I was told this is for non-physicists. Non-physicists generally, when they hear that someone's going to talk about quantum mechanics, become rather tense and nervous. So to put you at ease, I will repeat the quote to Richard Feynman, which is a flat-out statement that no one understands quantum mechanics. So you don't, and I don't, and Feynman doesn't, and she doesn't. No one knows quantum mechanics. So I don't think that's going to change from anything I tell you. So I feel no pressure whatsoever to make sense, and you have no pressure whatsoever to understand me. So you just go along for the ride. So you might say, look, if you don't know quantum mechanics and we don't know quantum mechanics, what's the difference? Difference is you don't know quantum mechanics and you keep your mouth shut, but I'm up here. So, but it turns out there is a small difference. The difference is that I sort of know how to do all the calculations using quantum mechanics. That's how we understand quarks and gluons and solids and liquids, and all the way up to formation of galaxies requires the laws of quantum mechanics. Unfortunately, I cannot describe them to you because I'm not allowed to use any mathematics, and that's what you need to do that. My hands are tied. Everything I know is no use here. So I have to find some way to go around this thing. That's very difficult. See, when you want to talk physics without mathematics, it's like trying to explain to somebody who has no knowledge of love what is so interesting about a play like Romeo and Juliet. So imagine a person with no romantic notion whatsoever. So let's say, for definiteness, a physicist. So you go along, and here comes this physics guy, and you say, hey, physics guy, what are you doing with your hands? You've been watching MTV, you got all these rap moves. He says, no, I don't know what you mean. I just want to remember that the electron goes this way. All right, so you sure you don't watch MTV? He said, I don't even have a TV. My parents gave me a TV, so it became well-rounded. Then I turned it into an oscilloscope and took it to the lab. So this is the person to whom you have to explain Romeo and Juliet. So you start by saying, Romeo and Juliet are in love, and he says, look, please don't use that expression, I don't understand. So you say, well, they have an attraction. And so now I understand. So it's the attraction proportional to the product of their masses. And you say, well, it's not so much the value of the mass as the shape that seems to be very important. So you realize you cannot have any kind of communication, and that's really my problem. And the only escape I have is that all physical theories, even if they're very mathematical, quite often make some statements which are about the physical world, which you can actually communicate to a non-technical audience. And they have the virtue that they mean the same thing to the expert as they mean to the non-expert. For example, in thermodynamics, there is a statement that there is a limit to how much you can cool things. You might think you can cool things forever, but we know you cannot go below minus 273 point something. Similarly, if you thought you can go as fast as you like, Einstein's theory says there is a limit. So quantum theory also tells you there are certain things you thought you could do, but you cannot do. I'm going to talk about one thing, at least, that we all think you can do based on our daily life, which is not allowed by the laws of quantum mechanics. And that has to do with the following phenomenon. So if I take one of these guys, you see it in one hand, and I throw it up in the air, and I'm supposed to catch it. I throw it up in the air, and I catch it. Suppose in between my throwing and my catching, you were sort of looking somewhere else. The question I have for you is, what do you think happened after it left this hand and landed in this hand? And the safe assumption is, well, it went from here to here along some trajectory. Maybe it went in a straight line, or if you're worried about gravity, it went up and it came down. But that's the assumption that turns out to be wrong in the world of quantum mechanics. In other words, if you have an electron that left an electron gun, and then you know it left because the gun recoiled, then it's caught on the other side by an electron detector, you know it came there because that one recoiled. What happened in between is the question. So the standard answer is, well, it went on some path. And what I'm telling you is, that assumption is actually incorrect. Now, you can say, look, if you throw something like this, even if I don't look, it has a path. What difference does it make whether I look or not? The answer, of course, is that in this case, somebody is always looking. And if you're not looking, there are other people in the room, there is light shining on the object. Even if you turn off the light, it's going through all the air molecules or bumping into some cosmic ray particles. Things are constantly observed. Then, of course, they have a path. What I'm telling you is, if you did not look at it strictly, by that I mean had no contact with the electron, then there is no reason to assert that it had to go from here to there on some trajectory. That is a wrong statement. Now, people, you can take the view that it's your word against mine on what happens when no one's looking. So you can say, look, why don't you keep thinking there is no trajectory? And I will keep thinking there is. It doesn't seem to matter. Well, it does matter, because if you make that assumption, eventually you will make a certain statement which is wrong, in the sense that if you do an experiment, you will make the wrong prediction. Now, that is not allowed in the world of physics. If you look at physicists in general, they don't seem to care much about anything. If you look at the dress code, for example, they tie something around the waist. One day it's a tie, the next day it becomes a belt, and their socks don't match. These are the stylish guys who wear socks. So there is complete laissez-faire in the world of physics. And actually that's true, but there's one cardinal rule. If you make a prediction, the prediction's wrong, it doesn't matter who you are, you got to take it back. So what I'm telling you now is that if you believe that particles have trajectories between observations, you will eventually make a statement which is wrong. You will run into an experiment where your way of thinking will make a prediction, and what you see will be completely different and irreconcilable. That's what you will have to, that's when you will have to concede that you have to withdraw the statement that particles have trajectories. So I will go into the details, but this is the main point. If you say what is strange in the world of quantum mechanics, it is that things don't have trajectories between points of observation, whereas we often think they do. So I'm going to now go to the first experiment. Okay, this is a very famous experiment. This is called a Gedanken experiment, which means a thought experiment. Einstein was a master of these thought experiments, and now all of us are becoming masters of thought experiments because we got no money for real experiments. We don't even have money for thought experiments. It's a very tough situation right now in my field. But this experiment is actually the one Feynman likes to use to illustrate quantum mechanics. So if you follow this, which is a stripped down, bare version of a real experiment, you will understand, if you're not familiar with quantum mechanics, at least one part of the quantum world which is very strange. My goal is not to make you comfortable with it, because nobody is. The goal is to make you as uncomfortable as we are, simply to tell you this is the way things are in the quantum world. So let's see what the strange thing is. So in this experiment, you have here a little electron gun that produces electrons. It's like the gun in the television set, with one difference. This gun is designed to emit electrons at a certain momentum. And it has a rate of emission you can control, a lot or a little, however you like. Then you can think of it as a top view of some experiment. So if you're looking at the room from the top, here is the electron emitter, and here is the detector that collects electrons. Every time an electron hits the detector, you hear a click. Between these two, you erect a wall impenetrable to electrons, except for two little holes through which particles may pass. That's your experiment. Okay, so the first part of the experiment is performed by blocking one slit, then opening this one, go to the back wall, put your detector there, wait for 1 hour. See how many electrons come. Keep on moving it. For example, if you sat there, I don't know how many X's there are, maybe 10. That means you got 10 electrons per hour. You put 10 X's. So you move up and down this, and you join all those little things in your histogram, and you make a curve. I want to make sure you all know how to read this graph. Usually graphs are drawn vertically, but here, that height from there to there is a measure of how many electrons come to that point in a fixed amount of time, which will take 1 hour, let's say. Now, the second part of the experiment is very trivial. You modify it by blocking this guy and opening this, and you get 10. Okay, the third part of the experiment is the following, and here is where, if you don't know quantum mechanics, you should participate in this little questionnaire. If you know it, I don't have much to tell you. I'm going to pick a certain spot, carefully chosen spot, marked X, where I got 10 electrons a minute when this guy was open, 10 electrons a minute when that guy is open. The simple question is, what do you think will happen if both are open? That's the question. Okay, so if you believe in the laws of Newton, there's only one answer you can give. That answer is, it's 10 plus 10 is 20. In other words, electrons were following a path that went like this. Those guys don't care if this is open or not. Some electrons went like this. They don't care whether that's open or not, so they keep doing their thing. You got to get 10 plus 10. Now, sometimes people worry that maybe those coming from here will bump into those coming from here. We can take care of that by reducing the intensity of this, so it's 1 electron a week. And you just got to wait 10 years at each spot. But the point is, at a given time, there's only 1 electron in the room, so it's not going to run into anything but itself. But I'm just saying, open one slit and do the count, open both and do the count, and that's the place which got 10 with each. And the point is that I can find for you certain locations where if you open the second slit, you get nothing. Now, this is a surprise, okay? You got to understand. For example, if there's not an electron gun, but a real gun, okay? And here is a Lawrence, and they are firing bullets at him through these two holes. Suppose one hole is closed. He's still in some danger. If you open the second hole, his first reaction's got to be that things got worse. Right? You got 2 different ways to die now instead of 1. So, in classical mechanics, it's very clear that opening a second hole can only increase the number of particles coming in. And yet, if you do the experiment, you get nothing. That is the heart of quantum mechanics. That is what is strange. That is what you cannot and do not understand in terms of classical mechanics. There is no way to avoid the conclusion that when you open 2 slits, you got to get the sum of the 2 numbers. So, this is the end of classical mechanics as we know it. You have to abandon Newtonian mechanics. If you believe in trajectories, that's the end. Okay, now, one reason you abandon laws of physics is that they often make very definite predictions. And you can falsify a theory, and this is a falsification of Newtonian mechanics. So, again, I remind you that if I got nothing there, and I open one slit, suddenly I get something. That's also very strange. Okay, now, what are the modern explanations for what's happening? There are 2 theories. Okay, one theory is called the conspiracy theory. According to the conspiracy theory, electrons are not inanimate point particles that do what they are told. There are some objects with higher intelligence, and they just talk to each other and say, you know what, when this guy opens both the slits, let's not just go there. We'll just screw around with his brain. We'll mess with this guy. That's one theory. The other theory is the one I'm going to talk about. This theory is still with the referees. It's not being taught anywhere except probably in the United States, where all theories are given equal importance. Okay. So the theory I'm going to talk about is more standard and widely accepted. So to find out what the new theory is, you got to continue with the experiment. After all, I picked one spot where you got nothing, right? If you got less than what you expected in some places, you can expect you will get more in other places. And that's really what happens. This dotted line is the sum of the numbers coming from the two holes. And the actual number has this pattern. So this is the pattern we understand. Not when you do experiments with particles, but it's a perfectly well-known pattern when you study waves. If this is a water wave, as seen from the top, there are a couple of properties of water waves, everybody knows. If you stand in the lake with your eye at the water level, the water does this. So we know that's a maximum and a minimum and a maximum and a minimum. It's got a wavelength, which is the distance from one maximum to the other. One thing I want you to notice for later use, that if you go half a wavelength, you do the opposite of what you were doing. If you were at +4, you go to -4. That's an important result. All right. So if you do the experiment now with one slit blocked, and you emit these waves that come from here to here, they'll come out of this slit, they'll form a little set of concentric rings. I want you to go far off here and measure the action. You want to see what the water is doing. So you want a water wave detector. So here's one way to do the detector. You see that? You take a rod and you put a piece of cork in it and you stick it in the water, and as the water goes underneath, up and down, this cork will go up and down, and you have to watch the amplitude of vibration. And you plot the amplitude all the way from here to here with this guy open. Okay, so what will you find? It's not very surprising that you will find something that is peaked in front of one hole, and if you open the second one, you will find something peaked in front of the other hole. But if you open both the slits, you will find that the amplitude for vibration has this oscillation. Now, no one is surprised when this happens with waves, because the wave knows how many slits there are, because the wave is extended, and it knows if you got one open, two open, or both open. So waves, no problem behaving in this fashion. In particular, if you go to this point, you say, how come I get no vibration of the water here, whereas I got something when one was open or when two was open? There is no paradox, because the signal coming from here to here and from there to here is not a positive number like electrons per minute. They have to add up. What the signal is really a wave which can say go up or it can say go down. So these two slits can tell this guy, one of them can tell it to go up, the other can tell it to go down, so they don't do anything. So with waves, this is a pretty standard phenomenon. No one has any problem. This is beating the same point to depth, which is to tell you that here are two waves that start in step. If you come to this location, carefully chosen that this is half a wavelength more than that, you will find the maxima and minima from the two sides come at the same time, so that they cancel at all times. And there are other places where they don't cancel. So let's go back to the electron experiment and look at this pattern we got. Here is the pattern, and you can say from this pattern, what's the wavelength of waves you associate with this side? You got to do some experiments, and the answer is that the wavelength is some number called Planck's constant divided by the momentum of your electron. This number is 10 to the minus 34. I didn't put any units, joules per poundel per BTU. Doesn't matter what it is, because 10 to the minus 34 is a very small number. That's all you have to remember. Okay. If you got 10 to the 34 units of money, I don't ask you if they're yens or dollars. 10 to the 34 of anything, you are in good shape. Likewise, 10 to the minus 34 in any reasonable units is extremely small. That's something you got to remember for a few minutes. Okay. In other words, if you put here some standard values of mass, 1 kilogram, 1 meter per second, you will get a wavelength like 10 to the minus 34 meters. which is incredibly small length. You have to bear that in mind. But once you go to electrons and put tiny numbers here, this wavelength is a reasonable size, roughly the size of an atom. Okay, so what I'm telling you is you go to the same experiment, you look at the wiggly pattern you get here, and you extract a wavelength from it, and you get this result by doing a lot of experiments. You find the wavelength is inversely proportional to the momentum of this electron. Okay. Now, I'm going to get the same result of this funny pattern here by a different procedure invented by Feynman. It's going to give the same result, but rather than talking about waves, it talks about something slightly different. Okay, so Feynman's procedure requires the law of adding vectors, which I really cannot in good conscience repeat for this audience. Okay. All you have to notice in this picture is that if we give you two vectors of definite length, say 1 meter each, their sum, defined by the usual rule for adding vectors, can be anything from 2 to 0. That's all we have to know to follow this quantum discussion. So now I'm going to give you the recipe given by Feynman for reproducing this pattern. It's only a recipe. He is not going to tell you any more than I could tell you why when you open two slits you get nothing in some places. He's just going to describe it to you in a way that doesn't directly deal with waves, but deals with his own way of doing quantum mechanics. That's the one that's most interesting nowadays for a lot of people, so that's what I'm trying to explain to you. So our job is the following. Here is the electron being emitted, and it's being detected at any point you like on that screen. Is there a way to calculate this graph? What does this graph tell you? This graph says wherever the graph is big, you get a lot of electrons per minute. Wherever the graph is small, you get few. When the graph is 0, you don't get any. Feynman will give you a rule for calculating this function. His rule is the following. So you first list the different ways in which you can go from here to here. There are two paths. One is through this slit, and one is through that slit. Each path is going to be given an arrow of length 1. Okay? Each path is going to be assigned an arrow of length 1. And you're going to add the arrows from the two paths, and the length of the resultant arrow, or when you square it, is proportional to the height of the graph. So the only thing I have to tell you now is, you already saw in the previous slide, when I give you two arrows, they don't have a unique length. The length depends on the angle between the two arrows, and that's the most important part of this recipe of Feynman. This has an arrow of length 1, that has an arrow of length 1. But I'm adding now two arrows. And the rule for adding them is the following. When the two guys take the same length from start to finish, you add the arrows completely parallel to each other. If you move slightly off the axis, if you go to a different location where one path is somewhat shorter, one path is somewhat longer than these two reference paths, then the arrow for the shorter path will rotate clockwise, and the longer one will rotate counterclockwise. By how much will it rotate, and that's the key to the whole formalism, the difference in angle between them as a fraction of a circle is the difference in path length as a fraction of the wavelength. In other words, if that guy is shorter than this guy by a quarter of a wavelength, then this angle and this angle will differ by 90 degrees, which is a quarter of a circle. So as you move along this line, one arrow will rotate clockwise, one will rotate counterclockwise, and you can imagine once in a while the arrows will cancel. They're not canceled, they're at some intermediate angle, and then you've reached a point where one arrow is rotated to the 12 o'clock position, other to the 6 o'clock position, their sum is 0, that's the place where you get nothing. That's the place where that length differs from that length by half a wavelength. And you can see this does reproduce this graph, and this is called the Feynman's sum over path. In other words, Feynman's procedure is, if you want to go from here to here and you got two paths open to you, the quantum particle takes both of them, in the sense that you need the contribution from both the paths to get the correct result of the experiment. So that is the fork that Yogi Berra was talking about. Remember, Yogi Berra said, if you want to come to my house and you come to a fork, you take the fork. Well, that's exactly what electrons do. They got two options and they take both. Now we all know that the way to do quantum mechanics is to sum over all the paths. If you have 3 slits, you will sum over 3 paths, you will add 3 arrows with suitable angles between them. So you can see that if you want the quantum mechanics to work, you really cannot assign to particles a definite trajectory. This particle does not have a unique trajectory. You should also not think that it really goes through this and through that. All those pictures are completely wrong. You only know it was here, you know it was there. This sum over path is a mathematical trick for reproducing the result of the experiment. It is not to be taken as the actual particle is splitting into 2 parts or many parts. Particle never splits. You see it here and you see it there, you don't see it anywhere else. This is all diagrams used to calculate the answer. So, here is a standard question used to calm down people who say, I do not believe your view that the electron can go through both the slits. So, you put a light bulb here. So once you put a light bulb here, it will somehow illuminate these 2 slits, and if a particle went this way, you will see it there, and if a particle went this way, light will be shining on it, you will know it went this way. Then you have to say, look, now I cannot escape the fact that the number coming here is the sum of the numbers going through the 2 slits. In fact, that's correct. If your light was bright enough so that every time an electron went here or here it was noticed, the resulting sum won't have any wiggles at all. The numbers will simply be the sum of the numbers going through 1 and 2. That's because you have actually seen the particle. You have actually located it. It's only when you do not locate it that it happens. So it turns out that if your light is not very strong and some electrons get by without being seen, those electrons will produce a wiggly pattern, and the ones that were seen will produce a flat pattern. If you add the 2, you'll get a small wiggle on top of the flat pattern. The strange thing about quantum mechanics is electrons don't have paths, but if you locate their paths, then they behave as if they have paths. But if you don't catch them, they behave as if they don't have paths. That's very strange, that things have attributes that do not have precise values till you determine them. Okay, so the fact that particles can go through many slits and so on is a rule that you should apply only in the quantum world. You should not apply it to macroscopic phenomena. In the macroscopic world, of course, particles all seem to have definite trajectories, and that's because they're being constantly observed. So I want to do the experiment not with electrons, but with an object that weighs about 100 kilograms. I want a machine that produces 100 kilogram objects. I got a machine that makes a lot of identical objects, and they go through the double slits. So what will happen if you do this experiment? If you really pull it off, okay, then you will actually get this tiny pattern. But there are 2 obstacles to actually noticing this pattern. First is, when this object goes from here to here, should not run into anything. No particles, no photons, no contact with anything. That's going to be very hard for a macroscopic body. So you will generally not manage to isolate your body from the outside world. That's the first reason you don't see this interference pattern. You're constantly finding them here, there, and there. You connect the dots, you get a trajectory. But if by some magic you manage to isolate this object, it will form this pattern, but the wavelength will be something like 10 to the minus 34 meters. And that is so small that you're never going to detect it. You realize that about 1 billion of them will fit into 1 proton. So you're not going to build a detector that can follow this wiggle. So the laws of quantum mechanics, in principle, describe everything. It's not that they work for some things and don't work for other things. But when applied to a big object, either you will never manage to isolate it, or if by miracle you isolated it, you'll get an interference pattern that is so dense you won't be able to observe it. Okay, so I just want to conclude with one final question. People will always ask you, make up your mind, is it a particle or is it a wave? And I think if you follow this argument, you should be able to give the following answer. If an electron, for example, is it a particle? The answer is, it's certainly a particle in the sense that when it's emitted, I get a recoil from one place, and when it's detected, I get only one detector going off. I don't get 100 detectors lighting up as they would if it was a wave that hit the shore. It's hitting only one point. So one point carries all the momentum, all the energy, all the charge. So that's a particle. On the other hand, it's not a particle that obeys Newtonian mechanics. Forget any mechanics. It doesn't even have any trajectory. It's a particle for whom the only way to calculate the result of this experiment is to associate with it a wave of that particular wavelength. Then do the interference of the wave or do Feynman's sum over paths, then you get this funny pattern. So the predictions of quantum theory will tell you that if you send 1 million electrons, they will form this pattern. If you send 1 million plus 1th electron, you really don't know where it's going to land, but you can give the probability that it will land anywhere on the screen by calculating this function. So the final thing to also remember is that the laws of quantum mechanics are statistical, and the predictions made in quantum mechanics are statistical. They're not statistical because you don't know enough about how you started. You know all that you can know, and yet this is all you can say. Thank you.